Okay, in this lecture, we're going to start our section 3.7 material on mechanical vibrations, where we'll start looking at some applications of the second-order linear equations that we've been looking at throughout chapter 3. So we'll see here that these second-order linear equations with constant coefficients that we've been considering throughout chapter 3 can serve as mathematical models for mechanical oscillations. And the classic example that we'll consider here is the motion of a mass attached to a spring. So let's develop our model for this mass spring system. Let us consider some mass M, which is attached to a spring which is fixed at one end. And there's usually a couple of ways that we can visualize this system. We could have some vertical mount where a spring is attached at one end to this mount, and on the opposite end of our spring we have some mass M. Or another way that this is sometimes visualized would be with a horizontal mount, where we have a spring attached at one end, and on the other end of this spring we have some mass M. And we're interested in modeling the motion of this mass attached to a spring if it's set in motion. So let's introduce some variable for the quantity that we're interested in. We're going to let y of t denote the displacement of this mass from its equilibrium position at a time t. So after we initially attach our mass to this spring, it will come to rest at what we call its equilibrium position. And y of t is going to denote our displacement of this mass from that equilibrium position. Now, the usual convention here is when we consider the vertically suspended mass, a downward displacement from equilibrium would correspond to a positive displacement, whereas an upward displacement from equilibrium would be a negative value for y. And in the horizontal mount, we have a right-hand displacement from equilibrium would correspond to a positive y, whereas a left-hand displacement would correspond to a negative y. So let's see if we can develop a model for the motion of this mass spring system. To do this, we're going to consider the different forces that are acting on this system, the first of which being the spring force. Now we know that the spring force follows Hooke's law. So let me say, by Hooke's law, I know that the spring force is proportional to the displacement. And it acts in a direction opposite of the displacement. So for instance, if I were to pull my mass downward, my spring force would be acting in an upward direction. So we would say that our spring force, let me denote it as F sub S, is some constant times the displacement y. And to indicate that we're acting in a direction opposite of displacement, I'll put a negative in front of this constant k and specify that k has to be positive. And this constant of proportionality k is called the stiffness of the spring. Now, the next type of force that we'll consider for this system would be a damping force. So in almost any realistic mechanical system, we have some sort of friction or damping present, say due to air resistance. And to model our damping force, we know, well, our damping or frictional force will act in a direction opposite of the direction of motion. And we usually assume that this damping force is proportional to the velocity of our object. So the more rapidly it's moving, the more damping is present, or the larger the damping. So here we assume that our damping force is proportional to the velocity of our mass and acting in an opposite direction of the direction of motion. So our damping force, let me denote it as F sub D, would be some constant, let's call it b, times the velocity, which would be the derivative of displacement. And to indicate that this acts in a direction opposite of velocity, I will put a negative in front of the constant b and specify that b needs to be non-negative. And this constant b is called the damping coefficient for our system. Depends on, say, what sort of medium that our mass is suspended in. And then the last type of force that we'll consider, or forces that we'll consider for this system, would be external forces. So any other force acting on this system is considered as external to the system. And these would be forces such as someone coming along and touching the mass, altering its motion, perhaps shaking the mount or the spring itself that the mass is attached to. So here, let me say all other forces are external to the system and are modeled by a function of time. Let me denote it as capital F of t. So our model of this system, as with most physical systems, follows from Newton's second law of motion, which says that force is mass times acceleration. So let's take a look at this. By Newton's second law, mass times acceleration, which would be the second derivative of our displacement function, is equal to the net resultant force acting on my object. And here, our forces were given by the sum of the spring force, which was negative ky, the damping force, which was negative by prime, and the external forcing function, f of t. So if we move everything to one side of our equation, or all of the y terms to one side of our equation, we have my double prime plus by prime plus ky is equal to f of t. So again, by Newton's second law, it follows that our equation of motion for this mass is the following, where m, b, and k are positive constants. Really, b is non-negative, since we could consider cases where there is no damping. So we see here that we have a second-order linear differential equation with constant coefficients m, b, and k. And depending whether or not we have an external force acting on our system, whether f of t is 0 or non-zero, we have a homogeneous or non-homogeneous equation. And we know how to solve these types of equations. This is what we've been considering throughout Chapter 3. Now, to complete the formulation of our model for this mass spring problem, we need two initial conditions. And these are usually given as the initial position, y naught, and the initial velocity, v naught, of our mass. So we would say that y at time 0, the initial displacement, is y naught, and y prime at time 0, the initial velocity, is this v naught quantity. So to start exploring the behavior of solutions of this equation, let's start with the simplest case of motion for this system. That is the case of undamped free vibrations. So let's start here by supposing that there is no external force being applied to our system, so that f of t function is 0, and there is no damping, so our damping coefficient b is equal to 0. So in this case, our equation of motion is reduced to my double prime plus ky equals 0. So we have here a homogeneous second-order linear differential equation with constant coefficients, and we know how to solve this. If we look for solutions of the form y equals e to the rt power, then r is a root of the characteristic equation mr squared plus k equals 0. And it follows that our roots would satisfy r squared is negative k over m. So r would be plus or minus the square root of k over m times I. We have complex conjugate roots. And for simplicity, this is sometimes denoted as plus or minus omega times I, where omega is equal to the square root of k over m. So in the case of complex conjugate roots for our characteristic equation, the general solution, y of t, would have the form c1 times cosine of omega t plus c2 times sine of omega t, where c1 and c2 are some constants depending on our initial conditions. Now, in the case that we're working with a mass spring system, it's sometimes convenient to rewrite the form of this general solution. So here we have a sum of sine and cosine terms of the same argument, omega t. And we can express this as a single cosine wave by making a change of variables. So let's see how it works here. If we were to change from constants C1 and C2 to new constants, I'm going to call them R and delta. Let's see how we could do this. So let's suppose that I set C1 equal to some constant capital R times cosine of delta, and C2 I will let be R times sine of delta. And let's see what our solution becomes then. Y of t would be given by C1, which was R cosine delta, times cosine of omega t, plus C2, which is R sine delta, times sine of omega t. So I could factor out a constant r from each term. And what I'm left with, cosine delta cosine omega t plus sine delta sine of omega t, is equal to cosine of omega t minus delta. This is a trig identity for the cosine of a difference of two angles. So when we rewrite our solution in this way, we're curious in how r and delta would be defined in terms of our constants C1 and C2. So here, solving for r in terms of C1 and C2, we can see that if we were to sum C1 and C2 squared, we would get r squared. And so r would be the square root of the sum of C1 and C2 squared. And to get delta, well, if I were to divide C2 and C1, I would have sine divided by cosine of delta, or tangent of delta. So depending on what the values of C1 and C2 are, we can determine our angle delta from this relation. So we see here, as we might expect, that our graph of this solution y of t is a displaced cosine wave that describes simple harmonic motion. So as we might expect, if there's no external forcing of this mass spring system, and there's no damping or no friction present, our mass will continue to oscillate, moving back and forth through its equilibrium position with a constant amplitude. So here we see a graph of such a cosine wave. And to introduce a little terminology describing this motion, we would say that this motion is periodic with a frequency of omega, and period denoted by capital T, which is 2 pi divided by omega. And the constant capital R describes the amplitude of this motion, and we denote delta as the phase. So here, thinking about delta, well, our solution was given by cosine of omega t minus delta. So delta is called the phase of motion. It's the displacement of our cosine wave from its normal position. So let's consider an example of a mass spring system which exhibits undamped free motion. In this first example, we consider a mass of 100 grams, and we're told that this stretches a spring by 5 centimeters. So if this mass is set in motion from its equilibrium position with a downward velocity of 10 centimeters per second, and if there is no damping, then we want to determine the position y of this mass at any time, and then find its frequency, period, amplitude, and phase. So for any of these mass spring problems, the first thing that we need to decide on is a unit for measurement, how we're going to measure our displacement. And reading through the problem statement here, it looks like some of our measurements were given in terms of centimeters, so let's stick with centimeters for our unit of measurement. Let me start by saying, let us measure our displacement y of t in centimeters. And here we're told in the problem statement that there is no damping. So since there is no damping, and we weren't given any information about an external forcing function, our equation of motion would have the form my double prime plus k times y is equal to 0. Our damping coefficient b is 0, and there is no external forcing. And we need to determine the mass m and our constant k, the stiffness of the spring. Now in the problem statement, we're given the value of m. Our mass was 100 grams. And so we just need to find k. So to determine our value of the stiffness k, we're going to use Hooke's law. Which says that the spring force is proportional to the displacement. So we have as we saw initially, our spring force is negative k times y, where k is some positive constant. So let's look at this. To solve for k, we would take our spring force, divide through by our displacement. And here our spring force would have to be equivalent to the weight of our mass hanging on the end of this spring. So we have our weight of this mass is equivalent to our mass times the acceleration due to gravity acting downward. So let's see what we have here. We have the mass, m was 100 grams, times the acceleration due to gravity, which is 9.8 meters per second squared, or since we're measuring in centimeters, 980 centimeters per second squared. And we divide by the initial displacement of our mass, and we were told that this mass stretched our spring by 5 centimeters. So evaluating this, we have 100 over 5, or 20, times 980, which gives us 19,600. So looking back at our equation of motion for this spring, we had the mass m, which is 100 y double prime, plus our stiffness k, which was 19,600 y, is equal to 0. Or expressing this in standard form, we could divide through by 100, giving us y double prime plus 196y is equal to 0. And then we compare this with the set of initial conditions. We were told that this mass was set in motion from its equilibrium position. So our initial displacement is 0 since it started at equilibrium. And we were told that we had a downward velocity of 10 centimeters per second. So the initial value for the velocity, y prime of 0, is a positive 10. Recall that a downward displacement corresponds to a positive y value. So let's go about solving this initial value problem. If we look for solutions of exponential form, y equals e to the rt, then r is a root of the characteristic equation r squared plus 196 equals 0. And so r would be plus or minus the square root of negative 196, which would be 14i. So our general solution would be given by C1 cosine of 14t plus C2 times sine of 14t, or y prime of t would be given by negative 14c1 sine of 14t plus 14c2 cosine of 14t. So now that we have y and y prime, we're ready to apply our initial conditions. Let's see what we have. Y at time 0 gives us C1, which we were told had to be 0. And then y prime at time 0 gives us 14c2, which had to equal to 10. So that gives us C2 is 10 over 14, or 5/7. So we find that our general solution, or our solution of this initial value problem, y of t, is given by C1, which was 0 cosine 14t, plus C2, which was 5/7 sine of 14t, where we were measuring in centimeters. So we have the displacement of our mass in centimeters after t seconds is given by this y of t function. And then we were asked to determine our frequency, period, amplitude, and phase. So let's look at it. Our frequency is given by omega, which was 14 in this problem. The period, denoted as capital T, is 2 pi divided by omega, so pi over 7. Our amplitude which we denoted as capital R. Well, we see here that our solution only involves this sine wave, so the amplitude of our sine wave, 5/7, is the amplitude R. And then our phase of motion is determined by tangent of delta equals C2 divided by C1. Now we saw here that C1 is equal to 0, so we're looking for values of delta such that tangent of delta would be undefined. That is, angles where tangent has a vertical asymptote. So we could take, for instance, pi over 2 as our phase. Now, another way we can think about finding that phase, if we were to rewrite our y of t function as a cosine wave by solving for r and delta in terms of C1 and C2, we could also write this as 5/7 cosine of 14t minus pi over 2. Because we know that a sine wave is just a cosine wave displaced pi over 2 units. So this would be an alternative way to express our solution there.